Thank you, Jeff. That was a great overview of our history, how we've come here, and where we hope to go in the future.
Is it short enough?
It was perfect. So we are going to delve into climate science basics, and to help us do that, we have Dr. Nick Silverman here from the Montana Climate Office. Dr. Silverman is a research scientist with the Climate Office that's on the campus of University of Montana in Missoula. And his research focuses on identifying hydroclimatic trends in mountainous landscapes. He's currently leading the climate analysis for the Institute on Ecosystems State Climate Assessment, which you'll hear more about tomorrow. And they have a table over there to tell you more about that state climate assessment as well. So Nick, if you'll join me up here, we'll turn the stage over to you.
Thanks, Jane. Good afternoon, everyone. Really excited to be here and be a part of what I'm sure to be a really great conference. I've been looking through the agenda, and the climate science team has put together just a really interesting and I think thought-provoking program for everybody, and I'm excited to be a part of that. So I personally kind of stumbled into climate science on accident. When I started my research at the University of Montana, I was really interested in streamflow trends. And the more I kind of started looking into streamflow trends, I found myself having to look into precipitation and rain trends. And the more I started looking into precipitation trends, I found myself having to look at climate models and weather station observations and projections and all this stuff. And I found myself asking some questions about kind of the uncertainty around our weather stations and uncertainty around our climate models. And really kind of started to ask this question of, well, if our uncertainty around this is larger than the projected change, what can we really say about that change, and where can we say it? And so that research sort of culminated, and these are the results of 3 years of my PhD research. And I know you're not supposed to put results in the introduction, but I'll go ahead and break that trend here. So basically what you're looking at here is western Montana. You can see in the background that purple and blue colors. Those are the projected change in precipitation. That's all increasing is what we're showing there. And then those little black dots, those are the areas where with our current climate models and weather stations, we can detect or estimate these changes accurately. So all the places without those black dots, those are the areas where we can't, because the uncertainty is larger than this projected change. So it's about a 30% detectability rate across the domain there, 70% we can't see. So anyways, this kind of got me more and more interested in these problems revolving around climate, and I transitioned more to the climate side of stuff and took a position with the Montana Climate Office about 1.5 years ago. So today, I've been charged with the task of kind of providing an introduction or probably a review or refresher course on climate science and climate change for everybody here. I've got 4 goals for this presentation. Hopefully they align somewhat with your own goals. The first one is I want to introduce everybody to the Climate Office. Hopefully you guys know we have one. If not, you do now. And then spend some time refreshing everybody's memory on some of the standard vocabulary in climate science, and then we'll take a look at the science behind that. And then probably most importantly, my goal is to give some context for the later discussions and presentations over the next couple days. So the Montana Climate Office actually used to be housed here at Montana State University, and it was retired along with the state climatologist Joe Caprio in 1994, and it kind of sat well, it didn't exist for about 4 or 5 years, and Montana is one of the only states in the country without a climate office. And in the late 1990s, about 4 or 5 years later, University of Montana decided, hey, we'll take that over, and they somewhat revived it, although it kind of just laid stagnant for, about another 5 or 6 years, and then at the time, Governor Schweitzer went ahead and declared it the official state climate office, but it really wasn't until 2010 when the University of Montana hired Mike Sweet, who's an information specialist, to sort of basically go out and figure out what does a climate office do. And so he started going around the country and meeting with different climate offices and really starting to gain some momentum in what this office should provide. And then it was 2012 when the College of Forestry and Conservation hired Kelsey Genso and Ashley Ballantyne to sort of lead up the scientific effort in the state climate office. And then, like I said, I joined about a year and a half ago now. So we are an independent state-designated body. All 50 states have a climate office. We are the one here in Montana. We're located in Missoula on the campus of the University of Montana, but our goal is to serve all of Montana. We are recognized in 2013 as the official steward of climate information. And our big goal is really to provide all Montanans with high quality, timely, relevant, and scientifically based climate information and services. So we like to view ourselves as a bit of an extension as well as far as climate information. Okay, so what is climate? Well, we'll start off with the basic definition. This is the one that the World Meteorological Organization gives. They say climate is the average weather patterns for a region over many years. And I think they say actually 30 years, but it can be probably at least 30 and potentially more if you have that information. And so what this looks like is if you have some sort of a climate variable on the y-axis there, and then you have time on the x-axis, this climate variable, maybe it's temperature or precipitation, goes up and down over the years. And from a climate perspective, what we're really most interested in is the average of this information. But we're also interested in the average variability of this information. So these are really the two big things that we focus on and what really defines climate. So there's lots of different climate variables. The ones on the left here you see, these are kind of the more well-known ones: temperature, precipitation, wind, atmospheric pressure, solar radiation, humidity. The list goes on, though. There's lots of smaller ones, maybe some that you haven't even heard of. And in fact, the World Meteorological Organization defines 50 of these climate variables. And these climate variables are then lumped together into different components of climate. There's the atmosphere, which is the air, the biosphere, which is the green stuff, the cryosphere, the white snow and ice stuff, the hydrosphere, the water stuff, the lithosphere, which is the rock and earth stuff, and then the pedosphere, which is the soil stuff. And these all interact together as components, and then within these components there's lots of interactions, and it gets complicated really quickly. And if we were to zoom in on maybe just the biosphere and say, well, what are these interactions here, it starts getting very complicated. And I won't go through all this stuff, but the idea is you've got solar radiation coming in, you've got long wave radiation from the atmosphere, some of it's being reflected, some of it's being absorbed. And then if you were to also look, let's just say, at the biosphere and how it interacts with the hydrosphere or water, you've got precip, you've got evaporation and transpiration in the vegetation, the soil, you have evaporation, you have subsurface flow and surface flow, and I think you get the point. Today, we're just going to kind of eliminate most of those interactions, but I think it's important for everyone to know that they exist, and we'll focus on temperature and precipitation. And this is generally what most people focus on, and it's what we really see and feel on our day-to-day lives. So what can we learn from climate variables? Well, first off, what we can't learn, or what we can't really study, is short-range stuff, like weather. This is a totally different topic, and not something that as climate scientists we really like to touch. But we can look at historical averages and how those averages change over time. And then we can use those historical averages and trends to maybe come up with some annual or seasonal outlooks. And then we can also look at how those historical averages may change long-term into the future. And so these are sort of the three areas that I'm going to focus the rest of the talk on. The first one being these historical averages and trends. So I focused most of this talk on Montana because I think we're all probably 95% Montanans here, and so I think it's kind of interesting to think of, we all know climate change is a global process, but we'll see how that impacts Montana. This is just a figure showing the mean annual temperature across the state of Montana. You can see the mountain areas. These are cooler colors showing lower temperatures, and then what you would expect, warmer colors in eastern Montana. And then down below, that shows the trend of average mean annual temperature in Montana over the last 100+ years. And you can see there is an increasing trend there. In fact, it's about 0.2 degrees Fahrenheit every 10 years. And so over the last 100 years, we're looking at about a 2-degree increase in temperature according to this data. And if we look at the similar plot in precipitation, again, you can see across the state, the mountains getting more precipitation than the eastern part of the state. And when we look at the trend over time, we don't see quite as interesting of a change there. In fact, we don't see any change from a statistical perspective. We see a lot of variability, but not a lot of change. So we can use this information, these averages, to start to guess what might happen on an annual basis or a seasonal basis. And I always like to say, if you don't have any other information, the best estimate of weather conditions at a location for any year is the long-term climatic mean. So if we don't know anything else, we can expect this winter will be like the last 30 winters. But of course, that doesn't give us really the certainty that we're looking for, and it doesn't do a whole lot as far as helping us make decisions. And so we can use climate variability, if we understand it, to maybe improve some of this information and improve our estimates around what might happen on an annual or seasonal scale. So again, if we look at a climate variable and how it changes over time, we can see that there's these different variability patterns, and some might happen on a year to 5-year basis, and some might happen on a 10 to 20-year basis. And the point is if we understand where we are in this natural variability, then we can make some better guesses as to what might happen. And probably the one that most people have heard of, this natural variability, is the El Nino Southern Oscillation, or ENSO. And hopefully you guys have heard, we're in a strong El Nino year this year. And so I thought I'd spend a little bit of time talking about what ENSO is, what El Nino is, and La Nina is, and then what this means for Montana. So this is sea surface temperatures across the globe. And if you want to see what El Nino looks like, it's right there. It's this big red blob. And that's the red is indicating a warmer than normal sea surface temperature, and the blues are indicating a cooler than normal. And when this area in the Pacific gets warmer than normal, we call it an El Nino pattern, and this affects global weather patterns and climate over the long run. And so this blob, sometimes it's red and sometimes it's blue. So it gets warmer than normal, and then it gets cooler than normal, and it kind of oscillates back and forth. And this is a plot of how that oscillates on the 2 to 5 year frequency. And right now we're in this warm phase, which is called El Nino. When it's cooler than normal, it's called La Nina. And so the question is, well, what does this mean for the United States and maybe more specifically Montana? And this is a plot here that shows the correlation of winter temperature, or on the left is temperature, on the right is precipitation, of winter temperature with this El Nino cycle. And so what it's saying is in these warm red and oranges, that means it's positively correlated. So as ENSO gets warmer, or we get more into that El Nino phase, temperature increases along with that increase. And then as the relationship with precipitation is the opposite. So as El Nino increases or it gets warmer, the opposite happens, precipitation goes down. So we can use sort of these long-term correlations with ENSO and the climate variability to make some guesses as to what might happen this winter. And so, our best guess is that it'll likely be warmer and drier this winter than normal. Although we say that, we emphasize the normal part here in that we expect it to be drier and warmer than normal, but not necessarily drier and warmer than last year, where a good part of the state had a pretty dry, warm winter that's really unrelated to El Nino altogether. So that's kind of the good news. It doesn't necessarily mean it'll be worse than last year. And the other good news is we're hoping that we kind of come out of these conditions in the spring and summer, or we're expecting that we will. Okay, so that brings us to long-term projections, and when you talk about long-term projections, you have to talk about climate change. And when we're talking about climate change, now what we're interested in is we have our climate variable over time here again, and now it's oscillating, it's moving back and forth over the years and also over the decades. But we kind of want to see past all this noise and look at how is the average changing. And then also, and sometimes most importantly, how is the variability around that average changing? So first, quick introduction and probably a refresher review to the forcings behind climate change. I think probably a lot of people have seen some sort of a figure like this before. But you really can't talk about climate change without talking about the greenhouse effect here on the planet. And the idea here is the Earth has an atmosphere, and we're lucky we have it, because without it, we wouldn't exist. Temperatures would be too cold. And this atmosphere traps the solar radiation and heat from the sun. And it traps it by these greenhouse gases that exist, carbon dioxide and methane and water vapor and others. And this heat is directly correlated with these greenhouse gases. And so as these greenhouse gases increase, so does the heat that's trapped in the atmosphere, and consequently the temperature goes up. And so here, we know pretty confidently that carbon dioxide is increasing. We have really good observational records. This is from 1958, showing carbon dioxide in the air and parts per million per volume here. And there's a very clear trend. And we know that the greenhouse gases make up, or carbon dioxide makes up about 82% of greenhouse gases. And so if carbon dioxide is going up and it makes up such a significant part of the atmosphere, then we expect this to have a significant impact on the heat that the atmosphere retains. But carbon dioxide isn't the only greenhouse gas. There's others. Methane and nitrous oxide are the other two big ones. Methane makes up about 10% of greenhouse gases, and nitrous oxide makes up about 5%. And these two are particularly kind of important in the ag world, because you'll see a large producer of these greenhouse gases revolve around manure and soil management. And so even though they're a smaller percentage, they're still important to think about how they might be changing or increasing over time. So hopefully you can start to see how these greenhouse gases might affect temperature, and why we show trends in temperature increasing across the globe. But you might be curious how this might impact precipitation. And so if you know that temperature is going up, and we look at, again, this is that same figure I showed earlier, showing the interactions between the biosphere and the hydrosphere. You can see if temperature goes up, that our evaporation and transpiration for vegetation, and then the evaporation from the soil will also go up. And this creates a decrease in soil moisture, kind of a drying effect on the land surface. But that water has to go somewhere, and that goes into the air. And so as temperature goes up, the ability of air to hold moisture also increases. So the air becomes more moist. But eventually it has to come down. And so it comes down at a greater rate. And so precipitation increases. And so you have sort of this kind of opposite effect. You have this wettening from the precipitation, and then you have the drying from the change in soil moisture. And this change, you can see this sort of across the globe, that some areas are, you get sort of a wetting effect, and others a drying effect. And this is a projection of the end of the 21st century of precipitation change across the globe. You can see the areas in blue are where precipitation is supposed to increase, and the areas in brown are where it's supposed to decrease. And generally what you tend to see of these types of projections is the areas that are wet look like they're going to get wetter, and the areas that are dry look like they're going to get drier. We're kind of in a transition zone here, which, lucky us, means we don't really know exactly which direction we're going to go in, so there's a large amount of uncertainty. So, kind of the big question is, how do we know all this change isn't natural? And scientists have been doing all sorts of experiments for a really long time on this one, because it's a really important question. And this is one such experiment that I think shows it fairly well. The black line here is the observations of global average temperature over time from I think from 1895 actually. And you can see it starts to increase around 1960. And so what these guys did is they used a global climate model, and they said, okay, well, if this is natural, then we should be able to model this using just natural processes. So they included natural variations in sea surface, sea surface temperature, natural variations in the solar radiation, volcanic eruptions, all these sorts of things that happen naturally. And that's what the blue line is. And you see, if they use just sort of the natural processes, that these the observations slowly sort of diverge from their modeling results. And the red line is when they add the human impact part, so the increase in greenhouse gas content and carbon emissions. And that's the red line. You can see that that lines up really well. And there's lots of experiments that show similar stuff to this, but this is one that I think it's a good example of how people are thinking about this. Okay, so we use these big global climate models that I talked about to do these experiments. And really, when I talk about climate models, I'm just talking about a bunch of physics and chemistry-based equations that take into account all those interactions and components that I mentioned previously. And they're usually done on some computer, hopefully a little bit newer than this one here. And the big part when we start looking into the future, we have to come up with some guess as to what society might do in the future as far as the carbon emissions and these greenhouse gases. And so one of the ways that this has been handled is through a big model intercomparison project called the CMIP5. 5 is because it's sort of the 5th iteration. And what this does is there's 20 plus, I think there might even be 30 now, teams of climate modelers from all over the globe that do their best guess at what might be happening, and they all do the same exact experiment. They use different representative concentration pathway scenarios, or RCPs. These are essentially guesses as to what carbon emissions might do over the next 100 years. There's 4 of them. There's RCP 2.6, 4.5, 6.0, and 8.5. Generally, let's see if I can get this arrow over. Yeah, there we go. Generally, people tend to use just the 4.5 and 8.5. We've kind of surpassed the reality of 2.6 at this point. 4.5 is suggesting that carbon emissions are tapered around mid-century, and then the 8.5 is a scenario where carbon emissions continue to increase throughout the 21st century. And so all these climate modelers and all these climate models, they all do the exact same thing, but with their different models. And then we look at the average of their results, and we call this an ensemble. And this comes out at a very coarse resolution because it's meant to be used at the global scale. But here, we're interested in what's going to happen here in Montana. And so you have to take this information and then you have to downscale it using some sort of statistics or physics to get it from a resolution that's maybe appropriate for global decisions or global answers, but doesn't do us much good here in Montana. And so this is just a figure that shows this downscaling and what it might look like. This is over California, but you can see here is these are kind of the resolution of those global climate models, and then when you provide the physics or statistics to downscale it, you get quite a bit more information. So I thought, as part of this climate assessment that we're doing for the state of Montana, I started to put together some of these downscaling results. So I thought I would share some of this with you guys. It's still preliminary, so take it with a grain of salt. Here's the results on temperature. This is the change in temperature when you compare 30 years of historical conditions with 30 years centered around the mid-century, so 2050. And you can see these are the 2 different scenarios, RCP 4.5 on the left and RCP 8.5 on the right. And both of them are showing pretty homogeneous increase in temperature. It's kind of boring. You just pick your shade of orange or red that you like, and the 4.5 is about a 3 to 4 degree increase, and the 8.5 is about a 5 to 6 degree increase by mid-century. But we can use this to maybe give us a little bit more interesting results. So we can look at the number of freeze-free days, or the difference in the number of freeze-free days between historical and mid-century. These are, again, the 2 different scenarios. Freeze-free day is a day where the minimum temperature does not drop below 0 Celsius or 32 Fahrenheit. So you can see here, especially in the RCP 8.5, that dark green, that's 70 days change in freeze-free conditions. So we're talking about almost 2 months that used to have minimum temperatures below 0 projected to not drop below 0. And that's, in the most extreme end, and, probably the average is around, maybe 20 to 30 days. And when we look at change in precipitation, you'll notice the scale down at the bottom, those are all positive values. So where the projections are for a positive, this is annual average of precipitation across the state, with the largest change predicted in the mountains. But we all know that an inch of precipitation in the mountains is a lot different than an inch of precipitation in eastern Montana. So if we look at this from a percent change perspective, we see that we kind of lose the change in the mountains, and then eastern Montana really stands out, upwards of 12% change in the RCP 8.5 scenario, or 12% increase, I should say. But again, this is average annual precipitation. That doesn't mean throughout the year we expect to see an increase. In fact, when you break it out by season, we see winter and spring, a pretty heavy increase between the 2 scenarios, between 10 and 20% there. But then in summer, we actually see a decrease around 5%. And so when we look at this spatially across the state, you see in the spring, we see this positive increase, and then in the summer, a decrease in precipitation. So there's three things, I have to be honest, that are missing from this slide, and that's why they're preliminary. One is, I'm really focused on averages right now, and we understand that variability is really important, and so that will be included in the climate assessment. Just haven't got to it. It's more challenging, to be honest, to look at variability. There's also no mention of uncertainty, which, like I said in the beginning, it's kind of one of the things I like to focus on, and I recognize that this doesn't have it included yet, but it will. And then the other thing that I've really left for the rest of the conference and for you guys is, what does this change mean? What does a decrease in summer precip mean and an increase in spring? What is 3 degrees versus 5 degrees temperature change? And that's the stuff that I think is really important, and I hope to kind of plant a seed in everybody here for the next couple days to discuss. So, in summary, what have we learned today? Well, hopefully we've learned climate is long-term. So if it happens quickly, it's probably not climate. The changes in climate, they really have to happen slowly for it to be climate. Temperature trends have increased over the last 100 years, and precipitation has not changed much over the last 100 years. We think that this winter will likely be warmer and drier than normal. Temperature is projected to increase in Montana pretty continuously across the state. And precipitation is also projected to increase across the state, but not in summer, where we think it will probably decrease. And the last thing is, I just want to emphasize again that I think it's really important that we use this conference and the remaining discussions, panel discussions, and presentations to think about what all this means. And I look forward to being a part of that conversation. I'll be around, and I think we have time for questions. Yeah, now. So I'm happy to answer questions now, and then I'll be around and happy to answer them in person as well. So thank you very much.
Let's take questions for Nick.
Hi, Nick. Great presentation. Steve Thompson from Whitefish. You've drawn a pretty clear line between climate and weather, but you didn't really address something that I've seen addressed as an indication of climate change, which is changes in extreme weather events. More heavier precipitation events. There's been indications of that. So it sounds like it seems to me there's a bit of a fuzz between weather and climate after all.
Yeah, I think, that falls under the variability part. So, if you go back to, or go all the way back here, when I kind of introduced climate change, and, you're getting at this change in variability. So, essentially that's the idea of, the average may be staying the same, but when we have a wet year, it's really, really wet, or when we have a dry year, it's really, really dry. Well, those average out to the same. And it's a really important point, and I actually get that question a lot when I give this presentation. And so that's why, I say I've definitely left that out. That's part of those three things that are missing here. The first one, so I haven't really focused on the change in variability. And we do expect to see that, and I think that's probably what you guys will be most interested in. And we hope to have that as part of the climate assessment that will be coming out in the next year or so.
For some of these climatic models, do they take into account biotic feedbacks like changes in evapotranspiration? For some of these climatic models, do they take into account biotic feedback? So with, say, CO2 fertilization and stomates causing a decrease in evapotranspiration, or are those effects just too small to be relevant at the scale which you're modeling?
That's a really good question. So some do and some don't, and it is really a scale sort of question. A lot of times what you end up doing is you take these climate models and then you use those as a driver in some sort of a land surface model. And that's where you really start to include vegetation and the dynamics of vegetation. And to be honest, a lot of those land surface models don't incorporate change, and they should, and there's been studies that have shown that when you do incorporate sort of this adaptation mechanism of vegetation, that our results change quite a bit from a water resources perspective. So it's kind of an active area right now of trying to incorporate some of those more dynamic features. But there are models that do it. Yep.
Sort of along the same lines, do the models you're representing account for extra release of methane from thawing tundra and those sorts of secondary effects?
You know, because I'm not part of the CMIP5 team, so I'm not running those global climate models myself. I'm kind of taking those results and downscaling them. I suspect they do, but maybe the answer might be similar to the one I gave before, which is maybe not all of them, and that's why it's so important to run 20, 30 different models and look at the ensemble, because some may account for it, some may not. All right, thank you guys very much.
Nick, I have a question for you. Could you tell the audience a little bit about some of the resources that are on the Climate Office, the Montana Climate Office website right now?
Yeah, so I did have those links up. Thanks for asking, Jane. We have two, well, really the big one is Mike Sweet put out a climate atlas, and this is now offered online. And those plots that I showed, the figures I showed of average temperatures and precipitation across the state, those are up there online at the website listed here. You can zoom in, click on a specific location, and it'll give you exactly what that information is. It goes way beyond just precipitation and temperature. There's quite a bit of information on that website. Mike's done a really nice job with that, and I would encourage everybody to go on there and kind of explore it, because it's too much to even go over here. But it really has a lot of information on Montana climate. And then there's also this climate variability app that I put together. It's not quite as refined, to be honest, as what Mike did, but if you guys want to check it out, you can. It allows you to sort of explore what El Nino, La Nina, and then there's this other oscillation, the Pacific Decadal Oscillation, how those impact Montana temperature and precipitation, so you can kind of play around. You know, this year you can look at, well, what does it mean during an El Nino year, but in a couple years from now, when you hear it's a La Nina year, you can use the same tool to figure that out. So.